Okay, and then we have the second paper in this session. We have already the author coming to the stage. It's Attributions for ML-based ICS Anomaly detection from theory to practice. And the presenter is going to be Clement Fang from Carnegie Mellon. The stage is yours.
Thank you. How does it advance? Just green? Is this the clicker? Is this the clicker? The green? Okay, gotta push it hard. Okay. Hello, good morning. Thank you for attending my talk. Today I'll be presenting our work, Attributions for Machine Learning-based ICS Anomaly Detection and Analysis from Theory to Practice. My name is Clement Fang. I'm a PhD student at Carnegie Mellon University. And this work is done in collaboration with Dr. Eric Zhang and Professor Leo Bauer, also at Carnegie Mellon University. Industrial control systems are composed of two parts: a critical physical process, such as water treatment or a power system, and an industrial controller. This industrial controller reads sensor values from this physical process and controls it by sending commands to actuators, forming a tight control loop. Because of their critical nature, these systems are often targets for attack. If an attacker is able to gain access to the industrial network, they can inject false values into the system by manipulating a subset of the feature readings in this control loop. What happens next is that when this controller reads this manipulated value and the effects are propagated throughout the system, the system may enter an unsafe or unstable state, causing damage and harm. To defend against such attacks, machine learning is a common proposal. By collecting a time series trace of sensor and actuator values over time, one can create a data set used to train a deep learning-based reconstruction model, which once trained can take a history of the ICS values and predict the next observed state. What happens then is at test time, when this attacker comes and performs the same attack by manipulating a sensor value, when this manipulated data is read or fed to the deep learning-based reconstruction model, its prediction and the next observed ICS state will differ significantly enough such that an alarm is then raised. In this work, we'd like to take this process one step further by asking how operators might actually diagnose or remediate once an alarm is raised. So the central question in our work is, when an alarm is raised, can we identify the sensor or actuator that was attacked? This question has been answered, or at least explored a lot, by the explainable AI community through what are called attribution methods. Attribution methods explain what specific input features cause a specific model to produce a specific output. In other words, when a model predicts a label, why? Take, for example, an image classification model and this input image on the left. When fed to this model, it might predict that the label is a goldfinch. And we might want to know which input pixels actually caused this goldfinch prediction. An attribution method would then produce an output corresponding to every pixel in the input, where each pixel would be assigned a score. And a higher score indicates that this pixel is more important to this goldfinch prediction. Analogously, when given data from an ICS and a deep learning-based model, if this model were to declare that there's an anomaly in the data, we'd like to know which sensor or actuator was attacked, causing this anomalous prediction. And we would like to use an attribution method to identify a component or a subset of the components in the system that were most responsible for this prediction. Hopefully, this would help with operator diagnosis and remediation. So in this work, we explore ICS anomaly attribution. We first ask how well prior off-the-shelf attribution strategies work for ICS anomaly attribution. After finding that they don't work so well, we then dig a little deeper and look into properties of ICS attacks and how they affect attribution accuracy. We do some analysis and find cases where attacks are well attributed and not well attributed. After discovering all this information, we then use it all to design a new method and ask if it's possible to do better than prior attribution strategies. So first I'll focus on the first question, which is just understanding how well prior attributions work for this space, for this task. Our work is the first to evaluate attribution in a large, diverse setting. So we compare across a variety of anomaly detection models, such as linear models and deep learning architectures like CNNs, RNNs, and LSTMs. We also compare across 3 different datasets. SWAT and WADI are 2 publicly available water treatment datasets generated from a real system. And TEP, or Tennessee Eastman, is a chemical process provided in the form of a simulator, which we modify for our work. When evaluating attributions, we evaluate over a variety of attack scenarios. SWAT and WADI in combination contain 47 real attacks, where the attacked feature and the behavior are all labeled. And we further systematically generate 100 synthetic attacks using this modified simulator to evaluate attributions. And the traces of these synthetic attacks are made available as a part of this work as well. So now let's discuss how prior work actually does ICS anomaly attribution. Given this input of sensors and actuators being fed to a deep learning-based model, the model would then predict what the next ICS values should look like. And these values are then compared to the next actual observation of ICS values. After performing this comparison, per feature errors, or a mean squared error, are computed for every feature in the system. And prior attribution strategies are simply just to point to the feature that has the highest error and identify that as the cause for the alarm or the one that was attacked. To build a little further on this, we adapt prior methods from the explainable AI, or XAI community. We adapt both local methods and gradient-based attribution methods. These are the 2 major families of attribution methods, and adapt them for ICS anomaly detection. What this looks like is that the entire time series input and the model itself are all fed to an attribution method as input, which then produces a set of attribution scores for every sensor or actuator in the system, again corresponding to how significant they are for an anomalous prediction. When evaluating attribution, prior methods just simply ask if the attacked feature matches the highest score. But we find that this is actually not how attribution scores would be used in practice. Our work contains a preliminary study of ICS operators where we surveyed them on their practices and potential usage of attributions for diagnosing alarms. From this survey, we had 2 findings. First, operators prefer to see multiple features, so not just the highest scored feature, but they don't necessarily want to see all features either. They prefer some automation in narrowing their search space when diagnosing alarms. Secondly, operators understand that there's a trade-off between the number of features seen and the overall accuracy of that output. For example, one operator reported that they would be willing to look at a larger output, for example, up to 10 features, if it meant that it was more likely that they would actually be able to find the attacked feature from this output. So to represent this potential trade-off, we propose a new metric called average rank for evaluating attributions. In this example, we're again looking at attribution scores for every sensor or actuator in the system, where each box represents a feature, and the darkness of it represents how high that score is. And we would envision that an operator would search through a top percentage of these highest scores before ultimately finding the attacked feature. And that's what the average rank is. It's the percentage of features that need to be considered when looking in rank order before finding the manipulated feature itself. And this also means that a lower average rank is better. If a different set of attribution scores were provided such that operators had to search through a smaller number of features, so for example, just 5% of the system as opposed to 20%, this would ultimately save them time, as they would have to consider a smaller portion of their system. So with our metrics defined, let's look at how MSE ranking performs when it comes to attribution. Prior work evaluates attribution on a few case study attacks by just showing examples where the highest feature actually has the highest MSE. But when evaluating this strategy across our full set of attacks and across all our anomaly detection models, the attacked feature has the highest MSE in less than 40% of all cases. Furthermore, on average, operators would have to consider at least 14% of their system before finding the attacked feature. So next we ask if our adapted attribution methods would work better. We identified, from a wide selection, we identified 3 best performing attribution methods for this use case, saliency maps, SHAP, and Lemna, and compared them to the baseline MSE ranking shown in black. And perhaps surprisingly, attribution methods are actually consistently worse than MSE at this task. So for every grouping, for CNNs, GRUs, and LSTMs, different anomaly detection models, the colored bars are consistently higher than the black baseline bar. So despite all the work that we did in adapting these methods and making them work for ICS anomaly detection, off-the-shelf attribution methods aren't yet successful for ICS anomalies. So that might be a bit discouraging, but let's take a look at this second question about how ICS attack properties affect attribution. We found that there are broad differences amongst the attacks evaluated, used for evaluation in our paper. They differ both in detection outcomes, for example, how long an attack takes to get detected or whether the attack is detected at all. And they differ in how the manipulation is performed as input to make the attack happen. For example, the magnitude, where in the system the manipulation occurs, or what pattern was used during the manipulation. In our paper, we analyze all of these factors, but in this talk, I'll just focus on 2 of them, starting with detection outcomes. So let's take the same results from the previous evaluation, but instead identify 2 subsets. First, let's look at the subset where attacks are actually detected within the first 50 seconds of the attack starting. And then let's look at cases where the attack was detected in that next 50-second window. And attributions are inaccurate within this first 50-second window, but actually improve when looking at this next later 50-second window. Every single method, the baseline ranking and all our adapted attribution methods, perform better. The average rank is lower, meaning that the operators would hypothetically need to spend less time looking for the attacked feature. Furthermore, our adapted attribution methods previously performed worse than the baseline, but they now perform better in this later timing setting. To illustrate how this is happening or why timing can actually affect attribution, I'll use an example attack from the SWOT dataset. So in these plots, the x-axis is time, and this attack is quite simple. Just one sensor is manipulated to a high unsafe value from this first dotted line marked anomaly start to the second dotted line marked anomaly end. And when this data is fed to a deep learning-based anomaly detection model, it's detected somewhat late, about 100 seconds after the anomaly begins, and that's marked by this exclamation mark dotted line here. So given this data, let's consider what options are available for representing this attack and picking the point to use for attribution. The first and perhaps most straightforward thing would be to do an instant attribution. This is to take the very first anomalous point in your time series dataset and to use attribution methods there. But if you actually look at the input window used for the model that precedes this point, it's completely benign. And this is a bad case for attributions. This doesn't work well in this case at all. The second option would be to do what we're calling the practical strategy. This is just to take the input window that precedes the actual point of detection. It's realistic since this point is actually flagged in real time, but it comes late. It's over 100 seconds after the initial attack began. A third middle ground option is what we're calling the ideal strategy. This is when the input window is shifted such that it contains only anomalous data, but is as early as possible. So the input window begins when the anomaly starts. Our input window is of size 50 for our models, so this would mean we're attributing the 50th time step. This is an ideal case, but it's unknown in real time actually when the anomaly starts, so this isn't a practical solution. Nevertheless, we'd like to compare how timing strategies affect attributions. We first find that this ideal strategy, so attributing the 50th second of every attack, actually outperforms practical outcomes. And this is because of this timing example that I just showed. But thinking a little further, if we were to take these early cases where the input windows contain some benign data and filter these out, this is what we're calling late detections only, then the average rank would actually improve. So for every method, by just removing these early timing cases, explanations or attributions perform better. So by avoiding these early timings, you can improve practical attribution results. Finally, I'd also like to consider cases where the attack isn't even detected at all. So these are cases where no alarm is raised and the detection is missed. We can still perform attributions at their ideal timing. And we find that our adapted attribution methods, SM, SHAP, and Lemna, perform approximately as well, whether an attack is detected or not. So even without alarms, attributions can be useful, perhaps for post hoc analysis of an attack. All in all, I'll summarize by just saying that attribution of ICS anomalies can improve when the strategy of when to attribute these attacks is decoupled from the timing of detection. I'll quickly go over the second factor that we analyzed, which is just the location or the type of feature that was attacked in an ICS. As a reminder, there's 2 major types of features in our systems. There are sensors, which read values from the physical process, and there are actuators, which execute commands sent to the process. And actuators are further divided into float-valued decimal controls or Boolean-valued on-off controls. And when comparing sensors to actuators, we see a big difference in which methods work best. Our attribution methods, for example, are far more accurate for these float-based actuators than for sensors. And the reverse is true where the baseline ranking method works well for sensors but works very poorly for actuators. Furthermore, Boolean valued actuators in our dataset are the most difficult to attribute for all methods that we've seen. This is just because that 0-1 signal doesn't have enough information for an attribution method to understand. So I'll summarize by just saying that different attribution strategies are best for different feature types. So now that we've done a bit of analysis on these cases, is it possible to do better than prior strategies? So without knowing what attack or where it's being executed or what timing strategy we're using, can one strategy be best? And we'll propose an ensemble of attributions for this. So given the same input of sensors and actuators being fed to a model and predicting the ICS state, we're independently going to compute the MSE, the saliency map, and lemma, and then take the average of those scores and report that as the overall attribution score for every feature. So when considering how well our ensemble method works, let's just consider each of these individual components first by looking at how their average rank changes as time passes from the beginning of an attack. So the MSE starts off well, it has a low average rank, but the average rank increases and begins to perform worse as time passes. The opposite is true for our attribution methods. So saliency map and lemma perform poorly early, but improve over time as attribution is performed later. And this is again because of that time series history needed for attribution methods. Finally, an ensemble of these methods outperforms all individual methods at almost all time steps. So considering across the entire time sequence, the average rank is the lowest for the ensemble attribution method over the entire time sequence. And this is true even at practical timings as well. So you don't even need to use this ideal timing strategy for this to be true. In summary, our work studies attribution methods for ICS anomaly detection. We find that prior performance is worse than reported. And this is because ICS anomaly attribution is actually quite complex. Both timing and feature types affect which methods work best and in which situations. But we find that an ensemble approach, at least for now, is the best way to balance these trade-offs. And our survey also revealed that although imperfect, attributions do have a role in helping ICS operators with diagnosis. Our work is open source and has passed artifact evaluation. So the attacks used to evaluate attributions, the simulator used to generate those attacks, and the code for evaluating and generating attributions are all publicly available. And I'm very happy to take questions. Thank you.
I'm wondering how this paper ended in attack session, but
yes.
Yeah, the question.
So excellent work, and particularly I like the idea of that you actually went and talked to some chemical engineers for a change.
Yeah.
One of the things that's interesting about this, I'm thinking about the direct parallels to threat hunting, and your point that the operators are willing to accept a large number of high-quality signals. Actually, let me step apart from that. Here's what was interesting. Your point about the timing, the 100 seconds, that the quality improved the longer it went. And so my question to you is, have you considered also the possibility that there is a time at which a decision has to be made?
Yeah. So this isn't in our survey right now, but it's definitely a consideration that matters, right? Even if attributions are really great, but it's the next day, that's probably not going to work for a lot of use cases. This is actually kind of future work, so we're actually doing an ongoing continued survey of operators about their uses of attributions. And things like timing or the acceptable latency is part of that, but it's not included in this work, to be honest.
Any further questions? Okay, then.
Thank you very much. Here, I couldn't understand how you relate the attribution to the actuator or sensor. Like, is this a relation between the features and the actuators? So, are you coming up with a different model for each actuator, or location information? What is the link?
Yeah, so the way our model is used is that just the values from every sensor or actuator get collected and just fed, like the whole data set just gets fed to the model at inference. So when you use an attribution method and it tells you which feature in the model was most relevant, it's a direct one-to-one mapping to at least a sensor or actuator in the system. You mentioned some conditional branching or like something to treat actuators more specially, because exactly, they have some behavior that affects the ICS itself. This is also actually ongoing work right now. But yeah, I agree that there are gains to be made by making a difference between sensors and actuators when it comes to diagnosis of alarms.
Okay, thank you.
Any more questions? I also have a question for you. It is maybe less relevant to the method you developed but regarding the attacks which you used in your data set. So at least in the example you showed here, you could see that the effect of the attack is kind of visible, right? You look at this chart, you see that there is a sudden change in the parameter.
Yeah.
So do those data sets consider also more stealthy attacks, like adaptive attacker who tries to change it like gradually and it is not so obvious in metrics?
Yeah, so exactly what you just said, the gradual changing, that is considered both synthetically by us and in these data sets. Mm-hmm. Even then, I would consider that to be probably the first version of a stealthy attack. We have a really small section in our work about like adversarial manipulations that are meant to be more stealthy. And there's other prior work out there that looks into this. But I think something as a whole this community needs is a better understanding of attack impact and stealthiness when it comes to the machine learning side as well.
Okay, thank you. Let's thank the speaker again.
Thank you.